Good morning, everyone. Okay, so you're at an impromptu talk because it wasn't planned. I learned on Sunday afternoon that I would be giving this talk, or a talk at least. So what do you want to do? I said, well, let's kill orcs together. Let's do something that's technical. So, because it wasn't planned, it's going to be essentially a slides-less talk. Like there's 20 slides, but there's almost no content in it. We'll be live coding all the way through, essentially. So it's going to be, we're going to code. So that means that you stop me whenever you want. I'll try to remember to express the questions out loud so that everyone understands, just in case, because I was warned by my friend up there that I should do that. I already wrote all the code, but I'm still going to write it today. So a code that's going to look almost like what I'm going to do because I'm inventing as I go along is already on a site where you'll get access to the slides too. So quickly, just in case you don't know who I am, I'm a father of 5. I have a lot of animals at home. I teach. That's what I've been doing for the last 25 years. I used to do flight simulators. I work with games people, which explains the title today, because I don't write games, but those I work with do. And the kind of thing I'm going to do today is the kind of thing they come to me for. So we're going to, it's a talk on memory allocation, really, and orcs are an excuse, to be honest. So I'm just gonna get rid of I'm gonna use the slides like this because I'm gonna switch between code and non-code all the time. Okay? So first, a few words on how these new and delete things work. For those, that's fun. Not again. What have I done now? Okay. What the hell? Okay, that's fun. So when it's not PowerPoint, I get nothing. It just hates me. I swear that thing hates me. So we're going to first take a look at how those new and delete things work to make sure that everyone's on the same page. It's going to be a very brief overview, of course, because I can do 6 hours on that thing, and that's not the plan today. It didn't give me 6 hours for some reason. You're so cool. And then we're going to use that. So for the generals of it, while we're just discussing together, your vendors provide you with good implementations of new, delete, and their friends' new square brackets and delete square brackets for the general case, and they're quite efficient and they're quite well done. You might be interested, if you didn't know about it yet, to know that in C++ we can overload these things and do our own versions, and that's actually quite useful because memory allocation is not a problem for which there is one optimal solution. There are good solutions in the general case, and there's sometimes optimal solutions for specific cases. Let's try this. I'm going to write in Visual Studio if it lets me. We're going to write in Visual Studio. Notepad++ doesn't like this thing. Okay? I just wanted to write code. Okay, so if it's not something you're familiar with at first, when you write something like this in your code, with args there, whatever it is, can you all see my font? Cool. So what your compiler really sees looks more like this. So something like x star p is the equivalent of operator new with size of x bytes, something like this with a cast. So it's a size something like this to end up with allocating memory, but a chunk of memory. So operator new does not create any objects at all. Its role is to find a location where you will put an object at the end. It will provide you, if it works, with a chunk of memory that is contiguous and big enough to hold what you asked for. It may be bigger, but it won't be smaller. If it fails, by default, C++ throws bad luck. The C++ implementations, they will throw bad luck. And you can make it so they give return a null pointer if you really want it, but it's a bother, it's not fun. Once you have that, you don't have any object yet, as you can see. You have a pointer that lies to you and points to a chunk of raw memory where there's no object, even though it says it's an X star. And past that, you construct the object there with something that essentially we call placement new. So something like new at the location where P is of an X, or something like this with the arguments there. So when you work in C++, you can put objects wherever you want in memory. You just pass a void star to it. If I was really rigorous there, I would be casting P to a void star, in this case, to make sure that nobody has overloaded you with other arguments to play tricks on you. So it's a two-step thing. You first find a place to put your object, and then you kind of paint the object into that space with your constructor. New allocates or finds a place, because placement new just tells you where to put the object, doesn't allocate anything. And then you paint the object there. Likewise, at a later point in your code, when you do something like this, in practice, the compiler sees that as a two-step thing. It first destroys what was in there, because there's presumably an object there, by doing something like this. So this, you can actually do that if you want. This turns, conceptually speaking, that object into raw memory. So there's still memory there. There might still be data, you don't know. But the lifetime of your object is done by that point. Once you've done that, then it calls operator delete on your pointer there. That frees the memory that was associated with it for further use. And it looks like this. Okay? So as you can see, operator new and operator delete, they are cousins to free and malloc in the reverse order. Okay? So this is kind of what happens. So generally speaking, your vendors provide you, as I was saying, with good implementations of these. But when you know what you're going to do, you can do better. So what I'm going to suppose today, because the plan was to talk about killing orcs, and some people don't care about C++, they're just here to see blood. So we're going to make an orc type, and we're going to suppose a few things, because if we want to do better than what the standard provides with us, for us, well, it's good to have a use case, because we're optimizing for something. So I'm going to help myself. I'm going to have a cool use case. Okay. So suppose you have this big fight coming in your game, and there's going to be elves and orcs, and they don't like each other's, you know, because at some point way in the past, an elf maybe said to an orc, well, you don't smell so bad today, and then started the fight. Yeah? It ended up badly. So at the end of your game, at some point, they're going to kill each other, and it's going to be a carnage. It's going to be terrible. And you want that thing to be quick and efficient. Okay? So when you know some things about your code, about your use case, well, you can use that information to get better results. Okay? So my suppositions in this case to make the code fun are going to be, we know the maximum number of orcs total that will be in the game. So we know the worst case, there will never be more than that. We plan for it. It's in our design. Okay? 10 million or something like that. And in this case, to make it fun, no shamans. Meaning that what's dead stays dead. Because otherwise the problem is more complicated and doesn't fit in our talk. Okay? But that's actually cool. That's actually cool, okay? Because it tells us things. It tells us that if we're wily enough, we can allocate the whole memory that we need at once, because we know what the worst case is. And we can give away chunks of memory sequentially, like we would do in the monotonic buffer, in a sense. But it's only good for orcs, though. It's not something that we want to do for any type. Like the elves don't have those properties. Maybe they have wizards of some kind, or potions, or whatever. But orcs are special in our case. They die well. This is really, really cool, okay? So to make sure that our synthetic and totally artificial benchmark, but still telling, is giving us proper information, we're going to make a few things, okay? So I will want to compare what the standard gives us with what we can do, okay? So I'm going to make myself a little macro there to compare both. Cool? When I said that thing, it's going to be my version. When I don't, it's going to be their version. Their being my vendors. So there. But I'm going to turn it off by default. So we're going to make some tests first, okay? This new project, I want to make sure that I have recent code. So it's C++ 14 by default with this editor. I'm going to put latest just to make sure I have all the goodies. and I'm going to run speed tests. So it's going to be with optimization on. Okay. So first, we're going to have an if there on homemade, just so that our display tells us what we're actually doing. Okay. I think I have string view somewhere. Yeah, I did. So I'm going to move that a bit further down, if you don't mind. I had planned to do that in Notepad++, but it doesn't seem to work this morning. Let's check the system. There we go. There. So if it's homemade, I'm going to keep for myself a version that's going to say I'm homemade, like this. String view literals. Cool. Oops. Otherwise, as I said, same code, we'll say it's the standard version. There we go. Same number of letters, false cool, makes for good displays. Cool? Okay. Now we need orcs. So we'll invent some kind of orc class just for the sake of the talk that we have today. Class orc, say like this. Now, we need to have some kind of vision of what the orcs are, but I don't really care what they are here today because I'm talking about new and delete. Okay, so we'll make something simple. Let's say that they have a strength. They tend to be strong. Strength, maybe, okay, number. Strength with TH in the right order, of course. Like this. They smell really bad. They have a name, but orcs, they don't have much of a vocabulary. So and I'm going to give them a default name so that I can avoid getting in trouble with them. So they can look like this. No? And they have intellect. So orcs. Okay? This is what it's going to look like. And just for the sake of it, I'm gonna put a default constructor there, even though I don't really need it, just for the sake of the example, to ensure that everyone knows that by default they're all going to look the same, because this is what I'm measuring today. Okay, they all look the same to me, as they said. Now, when I will write my own version of the way I allocate orcs, because I'm only concerned about orcs, I'm going to use a cool C++ trick, which is to make the new and delete operators member functions. So that will only apply to orcs and not to the rest of the types of my system, because if I write them as free functions, it applies to everyone. That's a different matter. Okay? I have something that's specific to this type. So it's going to be, though, for my homemade version only. Homemade. So when you write them by groups of 4 normally. You have to write new square brackets, delete square brackets for reasons that are probably outside of what I can explain today. But if you want to know more, come to me after the talk and I'll tell you why. Okay? It's interesting, but it would make the talk a bit longer. So something like this. So the signatures that you want look like this. Operator new with the size T there. The size T, if you're not familiar with it, in this case represents the number of bytes to allocate. So new has to give you at least that. Fair enough? As you can see, there's no type information because new doesn't know what it's going to create. It happens before construction. Okay? And the new square brackets has the same signature. You get the overall size in bytes of the array you're trying to allocate. So if it's an array of 10 integers, it's going to look like something like 40. Okay? And delete, in its most humble incarnation, looks like this. Operator delete takes a void star. So as you can see again, it doesn't know what it's going to destroy because it comes into play after the destructor has passed. So it's just freeing memory. It's an allocation function, not a destruction function. There's also a version that takes the size as second argument since C++14, but I don't need it today. They could do that. It can simplify some tricky maneuvers sometimes to know that, and there. Now, I won't be dealing with the array forms today, so I will just throw an exception if someone tries to use them, and I won't use them. Okay, I'm only interested today in the allocation of single orcs because, again, we have the time that we have. Okay? Cool so far? Questions? Because you can stop me anytime. So I'm not using them right now, but these are placeholders. And at some point in org.cpp, I'm going to write my code. Okay? I tried to make them all fit into a single file because it's easier for people to play with. I also need to know how many orcs I'm going to have at worst because that's the use case I was describing. So number max, let's say 10,000 or 10 million. So just so we understand each other, how big in bytes do you think an orc will be in this case? How much space does one orc occupy, in your opinion? 32, you said? Any other? 15? That's not possible.
16.
16? Okay, no. 24. It's going to be 24. So how do you see it's 24? So it's a 64-bit. I'm compiling for 64 bits. I have 4 bytes for my int in this case. It's a 4-byte integer. 8 for a double, but there's an alignment issue there. So doubles, the way I dispose my things, double is aligned on an 8-byte boundary. So there's 4 bytes of padding between the int and the double. So I end up with 16 at that point. Then I have 4 cars, a bool, and 3 bytes of padding there. So I end up with 24. Okay, just to make sure. If I went too fast, tell me, but it's going to look like this. You can test it out yourselves. There. Of course, depending on how big an int is on your computer, you might have different results. Okay? But in this case, it's a 4-byte integer. Yeah.
Did you want to null terminate your name?
It is. It is null terminated.
Right?
It's 0 filled because it's an array. So, whew, safe. I'm not going to be using the name, but that's deliberate. So it's a 4-character array. There's 3 characters in it. It's an aggregate, fills with zeros at the end. That's how C++ works. Cool, so we have something. Now we want to look at how the standard works with us. So it's going to be a very simple test. And if you're telling me real games are more complex than that, real games take months to write. Okay? So let's make it simple. So we're going to display the version first. Did I include format? Well, whatever. Format is cool, but let's make it simple. So version. So it's going to say homemade or standard version. That's a start. Cool. Now, I didn't say it, but I'm going to say it now. I'm going to measure the time it takes for me to allocate the orcs, and at some point to deallocate the orcs too. So I need to measure time, and the way I do this, those who have had classes with me know that, is this small function that I really like that takes a function and arguments, calls the function with the arguments, and returns a pair with the result of a computation and the time it took to actually perform it. Now, the result is not really important in my case, but I'm going to return something just to make sure that A, the code compiles, and B, the compiler doesn't optimize it away. Okay? So this is how I'm going to test stuff. It's kind of cool because I can test anything with a lambda. So I'm going to make myself a vector of orc pointers. Now I can hear you. Raw pointers are bad. I know, but that's what I want to test. I just want to make sure that we see how fast or slow the functions are. So I don't want anything around it. I just want the bare stuff to make sure we all see what's going on. It's going to be very safe. Don't worry, I'm going to be nice. Okay? And I don't want to measure the cost of reallocations in vector because I know what I'm going to reallocate in this case. Okay? So the vector is a vector of pointers. The space of the vector is not what I care about, so I'm going to reserve it right away. Cool? So reserve, if you're not familiar with it, it allocates memory but does not initialize it in the same way as operator new allocates memory but does not initialize it in this case. And I know how many I want. It's the number of orcs. So this is because I don't care about what vector does. I care about my allocation functions for the actual orcs, and the vector doesn't hold orcs, it holds orc pointers. Is that cool? Cool. So I'm responsible for what I'm going to allocate. So I better free them at the end. Okay, so now we're going to see how our standard provided functions behave. And I'll tell you right away to behave well for the allocation of orcs by default. So something like this. 0 because it's the first one, test, and I'm going to take my orcs by reference, and I'm going to actually create the orcs. Please stop. So something like this. So simple for loop, and I is 0, I different from the number of orcs, plus I, and I'm going to add to my vector an orc. Push back. And by default, it's going to do erg with no intellect, and very smelly and very strong. So this will tell me how much time it takes in a very synthetic way to allocate orc concon number max orcs. Now, this is good for the standard function. It's good for mine. It's very easy. You're going up in memory and allocating stuff. It should be fast. Indeed, it will be. So we'll see if we're lucky. Allocated. Now I need to return something. I'm going to return the size of my vector at the end. So orcs.size, which will be exactly number max of orcs in this case. Allocated. R0 is my result. Orcs in. And I'm going to write it in microseconds because it's still a pretty quick thing. So duration cast in microseconds of dt0. And since I'm using C++20, it's going to write the thing nicely for me. So this should give me a picture of the time it took for me to allocate all of those orcs using the standard provided new facility. Questions so far? Cool. Then there's the fight. So there's a carnage there. Sorry. So I won't display that if you don't mind, because there's blood everywhere and there could be children looking at YouTube at some point. We don't want to scare them, but there's been a fight. Okay? It's bad. And then you're at the end of the game, and then you want to clean up the orcs because, well, they're all lying around dead or whatever. So you need to kill everyone and to reclaim the memory. So let's do something similar there. Auto R1 DT1, easy test. And I'm going again to take my orcs by reference. I'm just going to kill everyone. So for auto P in orcs, delete P. So they're all pointers. I'm fine with that. And in the end, again, I'm just going to return the size of the vector because it hasn't changed. And it's going to make sure that the function is not optimized away by the compiler because it's a very tricky beast. And the display will be similar to that, saying how I killed them. So destroyed R1 orcs in DT1 microseconds. So I expect the numbers to be good. Okay? I do. The vector at the end on line 90 will reclaim its own memory, which has nothing to do with mine. Okay? I'm playing with the orcs. That one was holding space for the orc pointers, two separate things. And there's no orcs left. They're all dead. So let's see if we get good numbers. I'm hoping it works. Should be cool. Should be quick too. So we got actually pretty cool numbers. So 492, so almost 500,000 microseconds for the news and 220 microseconds for the lead. It's pretty quick. It's a good implementation. You'll see numbers that vary depending on your compiler, your machine, the context, but the order of magnitudes from one to the other will probably look similar depending on the strategies they have applied. Because the way we do new and delete, it's not standard mandated. But we don't say how to do things, we say what should be done. So let's keep that somewhere. I wanted to put that in Notepad++, but it doesn't seem to collaborate. So we'll use Notepad. Just for the sake of keeping track of what we've done. Okay? And I could run it many times. The numbers will sit approximately in the same order. That's what's important for me. So the standard implementation doesn't know about what we know, which is the fact that there are no shamans. And we know how many orcs there will be at worst. So we know things. That's cool. When we know things, we can do better, sometimes. How could we do better? Well, we could define homemade there to be something, such that our code kicks in at this point. Now, what we will do is write versions of these functions that benefit from knowledge. One way to do that is to do what we call arena-based allocation. So the games people do that sometimes. You change level in a game, and memory fragmentation is an issue. So sometimes they allocate a huge chunk of memory at first. They manage it as a whole. And when they switch from level to level, they just throw it away at once and allocate another chunk so that memory fragmentation is not an issue. There used to be cases where it was so bad that they had to soft reset the machine between levels to keep the game running. So it's a bad thing. So when you know how your scene will behave, you can, by scene, use that knowledge if you want. And it's used in other cases than in games, of course. So let's write a small arena. I'm going to make my arena a template because the concept is general. It's not tied to orcs. It's tied to number of elements and size of elements. But I'm going to write it this way. Class T for a type, and size T, N for a number of objects of type T. So this big N there is not bytes, it's objects. It's important to know, when you're writing allocators, the N factor is objects. When you're writing new and delete, well, in new, the N is bytes. So you have to know what your measurement unit is, just not to get such that you don't get into trouble. So let's call that an arena. It's a size-based arena. It's going to be very simple in this case. It's going to allocate sequentially. So a better name would be a good idea. But again, we have an hour to ourselves and it's almost halfway through. Many ways to do that. I'm going to take 2 pointers in there. So P where my stuff will begin and cur where I am right now. I'm going to distribute or give away chunks of memory in a consecutive manner. So I don't need to do more bookkeeping than that. If I was handling shamans and having orcs come back to life after a while, I would need, of course, more than this. I would need to manage holes in the system. When I will create my arena, I will allocate a big chunk of memory, cast to char star of, do you mind if I use malloc? I could use new also, it depends on what you feel like. So size of T times N. So my whole chunk of memory is allocated at once there. If it failed, I have a null pointer, I should check for it. I won't, okay? But you should, because malloc won't throw if it fails, it's going to give you a null pointer, and then you're gonna be in trouble after that. So that's said. And initially, I'm going to be ready to give the first block at the very beginning. So there's no args there. There's no T's either. It's just memory, but it's big enough memory for the worst case. Cool enough? Good. So I just allocated a chunk of 24 times 10 million, 240 megabytes. That's fair. Big fight. At the end of the arena, at the end of its lifetime, just going to destroy everything at once. Now, if you're telling me, whoa, what do you do with the orcs in the buffer? It's not my problem. I manage memory, I don't manage orcs. Managing orcs is the job of client code, it's not mine. To each his or her own. No? Good. So if I start there managing T's, I'm not helping. It's not my job. This is not the kind of code, the kind of class I would want to see copied around because it's an RAII thing. It's managing a chunk of memory. Sharing that introduces complexity in the system. So let's make this thing non-copyable. So bye-bye copy constructor. and bye-bye copy assignment. And I could make it movable, but let's not go there today. Cool. Operator like this. Cool. So non-copyable, the arena lives on its own. The services I want this thing to give me now, it's modeling consecutive allocation of fixed size memory blocks. So I'm going to give it two functions, two member functions. One will be allocate one, which will give me the next block that I can allocate. I should check for overflow. I won't, but of course, please in real code do that. Okay? So simply, Q is cur. Cur goes further in memory. Q. Okay. So I would normally, if I was more careful, make sure that that plus equal thing there does not take me overboard. Okay, but then you need to add the error management there. And again, this is a small talk. And when I free something, deallocate one, well, since I'm not really deallocating in this case, because that's not what I'm modeling, I'm going to write the function, but I'm not going to do anything with it. So these are the best functions. Those that do nothing are lovely. Don't you think? Awesome. So simple stuff, but it does work. As long as you respect the rules. I mean, you don't take more than you asked for in the first place. And you know that you're not going to recover the block that you've lost. Still cool? Cool. Now my orcs will need a tribe there. This is going to my tribe. So I don't want that thing to show up at link time or anything. I'm going to hide it. Namespace like this. And it's going to be an arena of orc with orc, I said, with orc number max elements. It's going to be my tribe. So this is the object that will manage the memory for me. And it's what my member functions, new and delete, will deal with in order to obtain the chunks and free them. It's a global. So line 87 constructs the object, which means it's where I'm paying for my malloc call. So I'm not paying for it further down the road. Cool? Cool. I need to write my functions now. So it's going to be fairly simple in this case, to be honest. So something like void star, orc, operator, new. Now I should check for the size, but between you and I am allocating fixed arc-sized chunks. I don't need to know. Okay? It's always going to be size of arc if I do things right. There's a caveat there. So in my code, it's going to be simple. It's going to be tribe, allocate one. When I need an arc, it allocates the space for an arc from that tribe thing. Cool. Memory is there, why not? As I said, the new square brackets, I'm not going to implement because I'm not dealing with arrays this morning. So I'm going to benefit from the fact that C++ lets me throw anything. Not doing this. Okay. Of course, in real life, be more careful than this. And my delete operation will respect, as Ben suggested this morning, the fact that the tribe is responsible for the allocation strategy. So I'm not going to suppose that I know. So I'm going to write my operator delete there. That takes a void star. And I'm going to call the arena's function. Tribe dot deallocate one, sorry. P. Even though it's a no up, I don't want to know about that. And I could do something similar with these square brackets. I'm just not going to do anything because it will never be called in my code anyway. Questions so far? It's a working system. Was it complicated? I'm not sure. As long as you know what you're doing, it's not that bad. The code should probably compile in this case. But the fun thing is it's using knowledge. See? So instead of writing a general all-purpose system, I wrote something that's specific to my use case. But I know what it is. And I'm not cheating. No, this is not a general thing, it's a specialized thing. Now, is it worth it? Well, I don't know, what do you think? The delete, please. It would have given me a better display with Notepad++ because this thing has no zoom. But as a reminder, this thing has 6 numbers. The first one is a 4. The second one is a 9. This thing has 6, please. The current one has 6 numbers, but it starts with a 1. So there's an interesting speed up there, isn't it? Cool. The delete part is also more fun because I get 0, but it's not a bug. I'm actually really doing no work. It's pretty cool. If you do the same technique, by the way, with the arena that I just did, but you make a singleton out of that, because some people do that sometimes, and you make it a Myers singleton, you will get a non-zero value there. The reason being that if you have a static variable local to your function, it's created on the first call, and it's synchronized such that if there's 2 concurrent calls at once, it doesn't get created twice. And that synchronization costs you something. So you will get a non-zero value. You will get benefits from this technique, but less. It will show up less. Okay? So maybe that's another point for Ben's talk this morning, saying, well, keep singletons to the minimum. You know, by making a non-singleton, in this case, I get better results. It's faster. It's still a global variable, but it's hidden somewhere and nobody sees it. Do you think the speed up was worth it? No. I like it. I like it. It takes no time. And you know what's better than speed in this case, really, really better, is that it's totally deterministic. Meaning that there is no code associated with finding in memory a location where I could put my orc. I know where it's going to go, and my allocation function takes fixed amount of time all the time. And so does my deallocation function, but it's null time. So it's pretty cool. That means that a technique like this can be used in embedded and real-time systems because it's totally deterministic in terms of execution time in both cases. Whereas your usual memory allocation systems cannot give you those guarantees because they have to manage holes and variable size blocks. But they're doing it well. But they cannot give you a ceiling on the time it's going to take to find a block. Cool? Cool. So, it's cool because going on, I'm going to be able to go a bit further than I thought I would. So, as we saw, let's start with this, and I'll add some stuff because it went faster than I thought, but that's okay, I have lots of stuff. This is the right one? Sorry, I have to find the right button. So we saw how these things work. New and delete are functions that do not construct or destroy objects. They find, in the case of new, it finds where the object is going to go. In the case of delete, it returns the memory to the system. They intervene and interact with constructors and destructors. So when you do new of something, it allocates and then paints the object on it. When you delete on something, it destroys the object, rips the paint, and then releases the memory that had been allocated in the first place. Placement new that I mentioned is a special case of new with a special signature that lets you put objects in memory wherever you want. It's the most important one of them all. But you have to know what you're using it. Vector uses that all the time in weird ways. So we did that. We wondered, why would someone want to do that? Well, as I said, I think at the very beginning when the screen was dying on me, that when you want a cool solution in general, the vendor-provided stuff works fine. They're good. When you have knowledge of the use case, you can do so much better sometimes. Think about stuff that's stacked related. So the last thing you allocated will be the next one you will destroy. Systems like the one I just wrote work amazingly well. They're really cool. They're usable in constrained systems too. That's nice. Now, our use case was this. We had an maximum number of orcs known beforehand and no shamans. The no shamans part is important because it means you have no holes to manage. If you have to keep track of the holes that you made in your arena, you need much more code to write. So you need to have a way to find a proper place to put the next orc when there's an allocation request. It might not be necessarily the last place where the place where you stopped allocating the last time, because if there are holes, you have to look through them. There's ways to do that, but there's trade-offs. There's things that are very fast, take a lot of space. Things that involve linked lists that you have to merge and unmerge and stuff like that. It's more complex. Okay? But with simple cases like ours, it's blazingly fast. Now, the benchmark we did was artificial, but telling. We put together something, a small string that told us if we were doing the standard or the non-standard version. That's useful when you're doing tests. A small function to test the code. We wrote an arc the way we wanted it to be. I could have added more stuff. I could have put a string in my arc, but that would have hidden things from the benchmark, because strings might do allocation themselves if I'm doing something, and that would obscure what I was trying to say. So I went with something simple. And the fact that it's 24 bytes is just for discussion. It could be any size, doesn't really matter, as long as it fits your needs. And I discussed quickly the fact that I was using member function overloads, which is what you do when you have something that's specific to a type. It's kind of rare, to be honest, but it's useful. If you overload the global ones, you affect everything. So it's cool when you're writing a leak collector or a leak detector or something like that, but maybe not for the general case. It could be costly. Then we wrote the test code, synthetic, and we saw why we did that. We created orcs with pointers, distinguished the allocation of the buffer in which the pointers were stored from the allocation of the pointees themselves. We made sure to create a baseline, check what the vendor-provided solution does. Seemed fast enough. Then we did an arena-based solution, to which I will return in a second. We use our knowledge to do a good job. And we ran the tests. And well, when I ran the artificial stuff on my computer yesterday, I got these numbers. So there's a one-box link if you want to compare. I ran these on GCC. But see, on GCC, I had the machine which was running was a good machine, so 23,000 microseconds or so, and 8,000 microseconds for the destruction. And on my solution, it went from 9 to 0, so it's a significant speed up again. So it's not tied to a specific compiler. It depends on the machine you're running your stuff on. I cannot point out enough that this is cool. But again, as I said, the deterministic side of it is even better than the speed side of it for the use cases I care for. So the links, of course, they work. You can try them out. There are things you need to be careful with when you're doing stuff like that. And these are the things I want to make sure that we all understand. I didn't check for overflows. I could have. It would have barely slowed me down. You know, it's an if to add. But the reason I didn't do that in the talk is that you have to decide, what do you do? Do you throw bad luck in that case? I've seen use cases interesting. I think it's at Bloomberg. When they do things like that, they allocate on the stack to do something similar. And when they have an overflow, when they ask for more memory than what they have, they just call an operator delete, the standard one, and just delegate. So they leak because they don't track it. They deliberately leak memory. Why do they do that? Well, it's because they know that they're going to close the software every day or so because they're working for the New York Stock Exchange. So they close things every day and they do management. And then say, okay, they log the leak and say, okay, we leaked today. How did that happen? And they fix the bug for the day after. So that's fine. And if you're leaking some memory in a day and you know you can fix it for the day after, it's manageable. Depends on your use case. Okay? Of course, if your software is running 24/7, at some point you're going to have a problem with that. Okay? So things to be careful for. The arena code. I mentioned that I didn't check for overflows, but there's another thing I need to mention because I think it's important. You might notice that I use T there, but the only reason I use T was because size of T. Okay? I use size of T there for the computation of the size of the buffer I'm allocating. And I use size of T when I'm advancing the pointer to the next place where I'm going to allocate. So it's tempting to say, well, since I only need size information, I will remove the T from the equation and put two size T's there instead. So the first being the size of one object, and the second being the number of objects. Now I didn't do that. Any idea why? Yeah, okay, but you could create your thing with size of orc still. But why would it be a bad idea? It would be confusing. You can end up with two types that have the same size and both try to use an arena. If you're trying to share the arena, they're going to share the space. And if they're sharing the space, well, you plan your thing for a number of elements. They're going to be fighting over it. You're going to be in trouble. Okay, so in this case, keeping the type information for T avoids bad problems, especially if you're using singletons in your code. Okay, you're avoiding the problem of an arena in an unplanned for way ending up being shared by two types that don't care for each other. Is that cool? Okay, so you have to be careful about this. And if there would be cool, the rest is fine by me. There are inheritance issues. And that's something to be wary about too, if you don't mind. The code as I wrote it in this case is dangerous. The reason it's dangerous is that my system is size-based. So I'm relying on size of orc to be size of orc. Now, if someone, you've seen, I guess, Lord of the Rings. Or if you haven't, you should. It's a cool movie. There are urukais there. Big orcs, very mean, more bright. You know, they can say words, grunt words, and they're tougher and stuff. So these urukai things, they're like orcs with more stuff, you know, maybe weapons or something like that. So if you make a derived class from orc and you call it urukai, and you add maybe only a single byte to it, it's going to kill my system in this case because the new and delete functions will be inherited by the derived class, and they will use the same stratagem, but the type won't have the right size. Okay? So if you're using something like this is what you want to do. Okay? To make sure you don't run into the problem of someone being funny and making a derived class from your class. The code seems to work until they reach something that's close to the limit of what you allocated. And then you start running into weird bugs and destroying stuff you didn't want to destroy. Is that clear? Cool. Since I have a little more time, if you don't mind, I want to say a few words about those things that I went very quickly over at first, just for those who have never played with this sort of stuff. What happens when new fails here? I think I mentioned it. But when operator new fails, normally what it will do is throw bad alloc. It could throw other stuff. You could have a battery length or something like that in some cases, but bad luck is what you expect. Now, what happens after that if the constructor fails? That's tricky, because if you look at the code from lines 4 and 5 in this case, you will say, oh, this doesn't seem exception safe to me because I have allocated resources. And if my constructor follows the allocation and fails, what happens to the chunk of memory I have allocated? That's a worry. You know? But notice that when we write code, we write it like this. So at once, it performs the allocation and the initialization sequence. And since you cannot be taken responsible until the completion of the whole process of the memory that you are allocating, if the allocation succeeded but your construction failed, the runtime itself will call operator delete on the chunk of memory, and you will never see it coming. There has never been any object to speak of at that point. The exception raised by your constructor will just fly out, and delete will free the memory that you had allocated in the first place. Is that clear? Cool. That's important because there's, again, because I have a little time, the placement new that I have mentioned earlier exists. Don't try to write this one. It works fine. But it looks like this, okay? If you look at the global level, the global operator new looks like this. So you have a size T. We don't care what it is, and a void star. And what it does in practice is just this. It does nothing. Cool? That's cool. So you do new at a certain location of an object, and as long as the memory belongs to you and you're allowed to write there, it paints the object at the place where you want it to be. You have a big buffer, you can paint objects in there. You wrote a driver of some kind, and you have the rights to write to that memory. You can paint your class that represents your driver into the space memory you want it to be, and use the object. If it was hardware, it maps very well. Okay? But you have to know what you're doing. Now, when you do a placement new like that, the new square brackets does the same thing. You won't call delete on your object. You agree with me? Because what will happen if you call delete after that? It will try to free memory, but you never allocated the memory in the first place. It will trash your system, won't it? This is bad. Okay. So supposing that you felt funny and you decided, instead of writing something like this, you want to impress your friends? And you want to show them that you can really handle memory like a pro. But if you handle memory like a pro, your code will be simple. Okay? This is bad what I'm going to write. So you're saying, I want the length of a string. So instead of writing string size type length, that takes a const char star. Of course, you could do something cool and much simpler than what I'm doing right now. Don't do that, you're bugging me. So someone could say, well, it's lazy, but I could just make a string out of it and call it size function. You know? Which maybe allocates. It's totally inefficient, but it's safe. We agree? Don't do that. If you want to impress your friend and say, I can handle memory, you could make it in a complicated way too. You could do it this way. There's a Q in the title. So you could say, okay, I'm going to make sure I can do that thing. I can make a buffer that's big enough to hold my string because I know how to do that. Initialize to 0 because I like zeros. They're all the rage these days. Aligned in memory in such a way that I can put a string in there, because otherwise when you paint your string and you use it, you're going to have surprises. And then I'm going to put a string there because I can. String S is a new at the location where buff is, cast as a void star. Do how to make things complicated? Where buff is of a string made from P. Now you're responsible for the memory. There's no RAI or anything because you're trying to impress your friends. You probably had too many beers. Now you get the length, of course. And then you need to free that memory. You want to free the string you allocated there. It's very important to you. But you don't want to call delete on S because there was never any allocation of any block for your string. There might be stuff done by the string inside though, and that needs to be finalized, doesn't it? Doesn't it? Better. Okay? So what you do in this case is, well, you call your destructor, of course. And then you return the length, which is a terrible way of doing things. But what I want to point out is that when you're doing placement new on stuff there, well, you had your memory. You never did any allocation whatsoever. Okay? That might allocate, but not because of you, because of what string does. Because you, in your case, you did not allocate. You placed the string in that buffer and nowhere else. It's yours. The buffer's on the stack. So you have to finalize the string before you leave, and that's not done with delete at that point because you did a placement new, you placed something somewhere, so you want to call the destructor without freeing the memory. Okay. But please don't do this. Okay? It's just to show you how these things there interact. Does that make any sense? It was well meant. I tried. As you know, this talk didn't exist until yesterday evening. Hope you had fun.